All right, so today we're going to talk today about power, statistical power. And my mouse doesn't want to connect. Oh, there it goes. Okay, good. So we care a lot about type 1 error, alpha. The probability of type 1 error is alpha. We care a lot about it. We obviously do because we, in fact, set the alpha level, don't we? Right? That's something we do. We talked about that the other day. I said we set alpha at 0.05 almost always. We probably shouldn't just use 0.05, but we do. Fine. But it's obviously important to us as psychologists using statistics as a tool that it's so important that we end up explicitly picking a number for it. Our software, in fact, gives us exact p-values. I think most of you, about half of you did the first assignment using SPSS, which is great. And if you've played with it at all, or PSPP, you can see that the software actually gives you, it will give you, if you've played with it a little bit, trying to do t-tests or something, it actually gives you exact p-values. So instead of giving you p is less than 0.05, it might give you p is less than 0.03164 to whatever. We obviously care enough about this that we want a p-value to, 4 digits of precision. It's important to us. And the question I guess I could ask is, why is type 1 error more important than type 2 error? They're both errors. Right? Remember the errors in hypothesis testing, type 1 is the false positive, type 2 is the false negative. There's also something called a type 3 error. Just letting you know that you might run into at some point. It's asking the wrong question. And that means the data you have don't answer the question you're asking. That's called a type 3 error. That's more of a design thing. And it hasn't really caught on. People talk about it. I kind of like it though, because it's like, doesn't matter how good your analysis is, if your design's bad and you're asking the wrong question, you're collecting the wrong data, it's an error. So, but why is it that type 1 error is more important than type 2? I guess false negatives, do we think they're worse than false positives? Or sorry, false positives are worse than false negatives. Do you think that? Because I don't think I agree with that. But it feels that way. I guess on the one hand, if you miss something, a type 1 error, someone else will pick it up. Okay. Sorry, the other way around. Sorry, if you have a false positive, someone else will come along and say it's negative, no problem. If you get a false negative, again, someone will come along, type 2 error, and fix it. So maybe that's the idea. I don't know. Historically, this happened, and I told you guys this last week when I talked about R.A. Fisher and how he and Tukey were working on these tables, and Tukey, just cables, telegraph. Fisher says, what percentage points of the F distribution are your graduate students working on? And he says 0.05. That's why we use 0.05. It's literally, that's it. All our methods are set up that way, but that's kind of a tautology, right? It's like, why are our methods set up that way? Because it's easier. Why is that easier? Because our methods are set up that way. So it's not exactly a good explanation. I will see that it's easy logically to understand the null hypothesis. I guess that's why. Because that means nothing happened, right? Or they come from the same group, the same population, or the two groups are the same. Those all said the same thing. It's easy for me to say, I can understand the idea of nothing happening. So that's the null hypothesis. So I guess maybe that's why. So if we set up this hypothesis, this null hypothesis, and say nothing happened, I can logically imagine that. So maybe that's what it is. There's another kind of statistics that I'm not going to talk about called Bayesian statistics that work quite a bit differently than philosophically they work differently. The numbers are pretty similar. And the way the hypotheses work is different in Bayesian statistics. I'm not teaching you Bayesian statistics, so don't worry about it. But in that case, it works a little bit differently. Okay. But with sort of classical inferential statistics, which is what we're doing, we can set up a hypothesis that nothing happened, the null hypothesis, and it logically makes some sense. Right? Bayesian works differently in that you say, okay, what's the hypothesis? And then you say, how likely is a violation of that hypothesis to happen by chance? So you actually look at let's something like psychics. If you say there's going to be psychics, if you're going to say that, 0.05 ain't enough. You better be damn sure they're psychics, because you're about to make an idiot of yourself. So, if there aren't any, or we're pretty sure there aren't, we set up what are called our priors in Bayesian statistics, and we say, okay, that's so unlikely, I'm not going to believe anything until it's like a 1 in 10,000 probability. It's the idea of the shifting, like I kind of talked about, it's sort of the idea of the shifting alpha level. But instead of that, you have these priors, like it's all very formal, it's just different than what we're talking about. But the way we do things typically is with just sort of classical inferential statistics, and if that's the case, it's easy to understand a null hypothesis. And if we were to start with the alternative hypothesis, we would have to say, here's how big the effect will be. Right? Because if we're going to, mathematically saying nothing happened, that's easy. We get a bunch of zeros, that's easy. Saying something happened, mathematically I got to say, yeah, and how big? What was it? That's where it gets complicated, because you have to say, I don't know. Right? That's why I'm doing the science. That's right. As I said, we have to think backwards when we think about power. Okay. Okay, so you get the, so far, questions so far? Does it make some sense? Okay. In the best of all possible worlds, we would, of course, maximize alpha, or sorry, minimize alpha and beta, with as many errors as possible. Minimize type 1 error, minimize type 2 error, and have the most power. Remember, statistical power is 1 minus beta. It's 1 minus the probability of a type 2 error. It's the probability of doing a correct rejection of the null hypothesis. Okay? So it's that bottom right corner of the matrix, the decision matrix there. Apparently. So again, power is the probability of rejecting HO given HA is true. Okay. This line, that's just notation, it means probability of this given this. Conditional probability. So does everybody understand that? Because if you understand that's what power is, the rest of this gets, well, it's still hard, but it's a little easier. Okay? Okay. So I'm going to show you a picture now. I know a lot of you have the notes in advance. You'll see that here's the picture that's worth 1,000 words. So let's look at this. What I want you to do right now is ignore the right distribution. Just pretend it doesn't exist. Just look at the one on the left. This is the null hypothesis distribution. See, u sub 0. And we make a decision if we get a value greater than alpha, or greater than this value where alpha is, we reject the null hypothesis. Right? Ignore the second distribution for a second. Remember in 2126 when you draw a little picture, did you draw a little picture? I hope you drew pictures. It's important to draw pictures when you do problems, when you're starting out at least. Yeah, I still draw pictures when I'm analyzing data, because why not? Okay. But pretend the null isn't true. Let's say that the alternative hypothesis is true. So, now we look at this. Now we're saying H1, H sub 1 is true. What's the likelihood of us making a correct rejection? Well, it's all this area here underneath this curve, okay? From the alpha point over is our power. We could, there's a whole big probability. See how big the probability of making a type 2 error is? Pretty big, actually. Right? That's the probability of saying nothing happened when something actually happened. We just got a number so low that we went, well, nothing happened. We don't have any evidence. Okay? Again, questions on this. Does this make sense? Okay. If you this picture basically is the whole lecture. If you get that, then there's just a bunch of math that's going to come, but it's all based on this. Put that over there. So how would we increase power? Gee, that might have been a question recently on a quiz. Well, you obviously know a few of them. Well, the first thing we could do, let's pretend we can do whatever we want. We can't, but let's pretend. Well, we could make alpha bigger. Let's just put it all the way over here at 0.5. That's ridiculous, but we wouldn't miss anything. Right? So you can see that if we moved this point, this place where alpha is over to, say, here, we'd have a lot more power. We'd also make a lot more mistakes, a lot more type 1 errors. We wouldn't make type 2 errors anymore, but we'd make, it'd be type 1 error city, assuming, null isn't true. We could increase the difference between mu1 and mu2, or mu0, sorry. So what I'm saying is we could take this distribution, just put it over here. Now, can we practically do that? Of course not. If you could do that, people would be lining up and worshiping you on Sundays. Right? You can't just move variables in the world. You can't affect nature like that. It'd be cool if you could. But theoretically you could, because again, the numbers don't know where they come from. So theoretically you could, but practically we obviously can't do that. But theoretically we could. Also, I don't know that we can make alpha bigger either. I said the other day that people don't discuss non-significant effects. 0.0504. People are kind of married to 0.05. It's changing. It's changing. The assumption that a lot of us made who teach statistics about 30 years ago when we were all starting out was, by the time we're getting close to the end of our careers, by then we'll be, no. So it's now to you guys, okay? So those of you that go on and do this for a living, please push back against 0.05. It's getting better, but it's not where I wanted it to be when I was 28. How old was I when that review came? 29. We could decrease alpha, or sorry, sigma. It's not alpha. Okay, how are we going to do that? Well, we could, well, if we're dealing with the actual population, we actually can't do that either, right? That's one of those things, again, if we could do that, we're a god. This now sounds like we got a whole bunch of dead ends, doesn't it? Because we can't really make alpha bigger. We're not gods, and we're not gods. Uh-oh. Now you know there must be something, or the class would stop now. There's gotta be something we could do. There's gotta be something. I know there's something. Spoiler alert, there's something. And that something is the variance. Remember you saw that variance there, right? We could decrease variance, make the distributions tighter. If we make the distributions tighter, they don't overlap so much. Overlap, bad. But we can't. Oh, but wait a second. Here's our in. We can't do anything to parent population distributions. We just can't. But we don't do analyses on population distributions. We do analyses on sample statistics, on sample distributions, on the sampling distribution of the mean, which is affected by the central limit theorem, which says that sigma squared sub x bar, that's the variance of the sampling distribution of the mean, is a function of n, right? Get those markers? I remember to bring markers, but I got a marker roadie, which is pretty great. Any of them doesn't matter which, unless you got one you really want to ruin. Okay. I'm not going to ruin it. I don't know why I said that. Okay, you know that sigma squared sub x bar equals sigma squared over n. Right? That's the central limit theorem just says that. And again, if that's not intuitive, and I hope it is intuitive, like the more subjects you get, the better your estimate gets, so the distributions get tighter and tighter. oh look, that's a sample statistic. We can control that. We can control sample statistics. We collect the data. Get more subjects. As n increases, what happens as n increases? So we're now going to take the limit as n approaches infinity of sigma squared over n equals 0. In other words, as it gets bigger, the variance gets smaller. As n gets bigger, the variance gets smaller. We can do that. That's the thing we can do, and no one's going to say it's not 0.05. That's my dumb guy voice when I talk like that, just letting you know. That we can actually do that. That's cool. We can actually do this. Okay? And central limit theorem is what tells us why. Because of that. So we now need a way to try to figure out how many more subjects should we analyze? How much more data should we collect? Because at some point, like there's diminishing returns, right? Like every single person or rat or whatever the hell you're testing, every single data point you get gets you closer and closer to the whole population. You're making your n approach infinity, right? But at some point, if you've already tested 30 people, does that 31st person help? Maybe not. Is it not worth it? Maybe you get I bit my tongue. I'm gonna go hit something. Just a second. It really hurts. Okay. Ouch. When I was teaching in Newfoundland, I took a overhead projector acetate. Like they have a tissue paper kind of on the back when they're new, and I just made a new one, and I slipped it apart. But of course, I look at things closely because I can't see, and it sliced my lip. The acetate. You think paper cuts are bad? Do it with an overhead acetate. So I'm standing there, and I'm in front of like 150 people lecturing, and there's a great big screen, really big, and there's blood just going boop. You can see like drips of blood on the screen. It was great. And then I happily had some coffee. So I said, well, I guess I'll cauterize the wound. So I lip like this. And I swore, and I said horrible things. And I mean things that I shouldn't have said. Like, nothing like just saying fuck or something. Like, I said things that I don't say around people. So I then went to right to the dean's office, and I walked up. I said, so I just cut my lip when I was lecturing, and you may hear reports of a lot of swearing. I said, and they're all true. You know, but I really hurt myself, okay? Like, yeah, fine. So, but I thought, get out ahead of it, because there are things that I said I shouldn't have said. Okay. Anyway, back to this. Not bleeding, at least. We have to find a way to put a number on how much overlap. Remember, the overlap's the key thing, right? Because if we can make the two things not overlap, it's great. So let's see if we can get some way of standardizing this. So the effect size is going to be the alternative hypothesis mean minus the null hypothesis mean. And we'll have to standardize it because, you know, things have different scales. So we're going to call it D for difference. And we're just going to take the mean, you know, mu sub 1 minus mu sub 2. We're just going to divide it by the variance, standard deviation. And that gives us what we call D. Okay. Now, the thing about D is, how are we going to get that? And how are we going to get that? Like, how do we get mu sub 1 and how do we get sigma? I don't know. Well, the best way is probably prior research. So just look at old data. And when you're doing a paper, you're writing a paper or doing an experiment, when you're doing your honors thesis next year, you will have to go into your like you're doing a literature review, you're going to look at old stuff and find out what the world looks like. What are sort of standard sizes for these for values for D and U sub 1? That's one way to go. That's what people typically do. Of course, the question you have to ask yourself is, how big is big enough? How big of a difference matters? Okay. I guarantee you that there are all kinds of differences between, I don't know, left and right-handed people. There's tons of them. The biggest one is one's left-handed, one's right-handed, but there's others. And you know what? The differences are so small as to not matter. They may be even statistically significant, but the fact that the difference itself is so small, I don't even know what these differences would be, by the way. I just picked a characteristic for humans. We could have gone with sex differences, we could have gone with anything. There are differences, but they're practically meaningless. Okay? So something can be statistically significant and practically not significant at all. I bet you there's a correlation between the size of your little toe and your earlobe. I guarantee that's true. I don't know that, I've never read a thing that says that, but it must be. The bigger you are, the bigger your parts are. But does that matter? Does that say anything about human development? No, but it's probably true. In fact, it's almost certainly true. So you got to realize that sometimes you'll find a difference and say, well, how big is big enough? And this is the question when my honor students and we do a power analysis when they're sort of figuring out how many observations, how many subjects they want to use in their experiments. I usually say, look, if we collect enough data, we'll find what you're looking. We'll find something. Why don't we test everybody in the world? We'll find something. But it's not practically important. So how big's big enough? And it's, to me, I'll show you how big I think big enough is supposed to be. And that's what this guy Cohen was coming up with. The idea of how big is big enough. Well, let's first of all quantify this. So a D of 0.2, that remember D is mu sub 1 minus mu sub 0 over sigma, right? So just to keep that, put that up here on the board here. Victoria, if you want to remind me to bring my markers next, just send me an email saying Broadbeck markers. I will not forget markers ever again. Don't feel bad about doing that either. I'm asking you to do it.
No
unless,
problem with lending you them. So
okay, or unless you want to be my marker roadie, that's also great. Okay, this is this column. So let's look at this. So 0.2 D, the overlap, 85%, they're on top of each other. Who cares? To me, a difference that is so much that 85% of the null and alternative hypotheses distributions overlap is probably meaningless if it's some behavioral thing or some cognitive thing. If it's something about some horrible disease that'll kill you, yeah, that means. How many of us here are dealing with curing cancer? None of you are. So let's move on. There's no life and death stuff with anything that we're going to be doing. Somebody might use something you did someday to help some people. That would be great. I mean, honors thesis data. If you go on the grad, maybe you'll get a Nobel Prize. That's not, but I mean, your honors thesis when you do it next year, you're not blowing the lid off anything. And that's, most research doesn't blow the lid off anything. So I'm not trying to downgrade anything you all are going to be doing. What I'm saying is, you're not curing cancer. So a difference of 0.2 doesn't matter. Look at this. Even what Cohen called a medium-sized effect, 2/3 overlap. And that's the one typically people go, yeah, that's good enough. But even a large effect, there's still more than 50% overlap. So you typically probably want something between a medium and a large effect. What Cohen calls a medium and a large effect. Just realize that there's a lot of overlap, even with medium and large effects, okay? Again, we're dealing with, by the way, this shouldn't surprise you, typically in psychology, what are we dealing with? Complicated variables that have many, many inputs and many outputs. We're dealing with multiple causation. This is a hard science. It's hard because we can't just put things in a beaker and shake them. Right? What we use hard. What they use hard too, it's fine. The chemistry's fine. You guys are great. Nobody has to wash their eyes out after doing a psychological experiment. Well, depending on what you're looking at. So it's not surprising that we get fuzzy differences. Like that. Don't think of that as a put down of psychology, but that seems pretty damn small to me. I mean, medium is still pretty small. So just keep it in mind. All right, so let's do something with this. That's something being put in my nose back where it belongs. There we go. So now, what are we going to do with this? We're going to combine this information with the effect on sample size. We're trying to figure out how many subjects in an experiment. We're just trying to figure that out. Because like I said, and you'll find this next year when you're doing your thesis, especially if you run your experiments one participant at a time, which very often is the case, in fact, almost always. If you're testing groups of 20 people, you put 5 more people in each group, doesn't matter, it's easy. Just 5 more things to print out, you hand them out. If you're testing 5 more people and it takes an hour to run your experiment, that's 5 more hours of your life. It would be nice to not test those 5 people if we didn't have to. So let's not test them if we don't have to. So let's try to find out what the optimal sample size is going to be. So we have this thing called the delta statistic. That's a small Greek letter delta. Okay. Okay, so that's the small Greek letter delta. This is the delta statistic that is used to do power analysis. What the hell does that mean? Actually, if you think about math again, back when you were in high school, you look at, oh, I know what that means. Delta equals D, where's D? Times F at N, times how, basically what it's saying is D times how N affects the variable. We want N in there so we can figure out what N's going to be, right? So that's why N has to be there. So it's D times how N affects that variable. Okay. It'll be clear in just a moment. All right. So here we go. By the way, you never do these calculations. There are tables that you look up. It's cute. It's easy. You don't have to actually do this by hand. So f at n, as it says, how n affects a given test. So for a t-test, f at n equals the square root of n. Because think about what a t-formula says, and you all know this, that a t-formula says, let's do the most basic t-formula. What's n? Oh, it's square root of n. It's right here. There's square root of n. Good, I can throw that in there. That's what's affecting things. Square root of n. Okay. All right. This is actually not as bad as it sounds. If you know D, I got that in little scare quotes because you can never really know it. You're guessing based on past research or what you think is big enough. Usually you don't use past research. Usually what you do is you say to yourself, 0.5 is good enough. 4.8 is good enough. Because you know what it represents, and you know how much overlap there is. So let's say we know D is 0.5, or we only care if it's 0.5 or bigger. We only care if there's less than 67% or 67% of overlap. You usually just pick 0.5 because it's in the middle. And let's say we want a power of 0.8. So we want to be able to say that if the null hypothesis is false, we have an 80% chance of detecting that. And that's pretty good. That's pretty good. And there's an appendix in your book called the Appendix Power, which I'll show you how to use in a sec. And you have these values and you just look it up. Like it's really. So let's take a look here. Whoops, what's going on? Again with this. Where are we? Okay. So all we're doing is using another table. So if d equals 0.5 and 1 minus beta equals 0.8, remember, we said those things. We picked those things out of the air. Right? We said that's big enough and we want a power of 0.8. So these didn't have to be calculated at all. Alpha is 0.05. We don't calculate that either. We pick that. This is basically saying what n will do this for us. All this table is going to do is say how many subjects do you need? So here's the table. Now, I'll zoom in on it in a second, but you can see there's various, so there's the different alpha levels, and there is the delta level, and then in here is we have the power. So if we say 0.05, that's good. Let's actually just do it like this. 0.05, let's move that out of the way. So 0.05 and 0.8 power. It's right here. Delta is 2.8. We didn't have to calculate a damn thing. Okay? Now we know what delta is going to be, and we're going to sub it back into a formula and find out what n is. Okay? So it's literally, you get all the stuff you know, so that's going to be the size of the effect, that's going to be d. Then we also need to know the alpha level, it's going to be 0.05 almost always. Right? And we go from there, just look it up. Oh, and 0.8, let's say, 0.8 power, let's look up 0.8 right there. And you're going to say, wait, Dave, let's pretend. Let's pretend you wanted a power of 0.82. I don't know why you'd want that, but so you go, okay, well, there's two ways you can do this. You can go, I want to go up to 0.83, or you could say, let's see, 0.8, 0.83, you could like do interpolation if you wanted to. Fine. You know what I'd do? I wouldn't do that. I would just say 0.8's fine. Okay. Okay. And we just sub it into the formula. So, how do I do that? I just rotate, like I cross multiply. This isn't complicated. Okay. So n equals delta over d squared. Let me just go back for a second. Let's go back to the formula. I'm going to come back for a sec, and I'll show you. So, where we got this from. Okay. So there's our delta. Because I didn't show you how I went from that. So we're going to go delta equals d at f at n. So, as I say here, again, f at n equals sigma squared sub n. Sigma squared, is that right? No, just square it up. Right, so we're going to do that. O times d. Okay. So now let's go back, forward again, back, forward. That's good, Dave. So that's where we were, blah, blah, blah. And again, remember, we set all these things. We did it. We didn't have to calculate anything. The only time you end up having to do any calculation at all is when you come, again, we set that up. We want 0.8. We look it up in the table. So we go, okay, it's this column here, the second one over. And we want to look for a 0.8. There it is. We come across our delta is 2.8. Just to show you again, you can see that there it is, 2.8. So you see the 0.8 in the table, you read across, you see 2.8. Now, what did I do here? I'm trying to get n. So what I did, well, I don't need square root n, I need n. So I squared everything. Right? If I isolate d, right, it's going to be this over n. So it's 2.8 yeah, so the D ends up here and here, so I did that wrong. Yep. So that's going to be the delta there. And it's this whole thing squared. 2.8 over 0.5 squared. You do the math, that's 30, we need 31.36 subjects. 31. Oh, let's go with 32, let's round it up. We need 32 subjects. For a 0.8 power with an effect size of 0.5. So you'll see a lot of times people will say, I'm just going to use 30 observations, and that's fine. Because it actually, there's a reason people use 30. It's because, oh look, it gives you 0.8 power. What if we increase the power? So I'm going to increase the power to 0.99. If we're going to find something, it's going to be there. The new delta value, and I'm not, learn how to use the table. Look it up at the table. You look for 0.99. It's now 4.2. 420. I was hoping when weed was legalized that people would stop making 420 references, but it didn't stop. I hope lots of things. Hope springs eternal, if you will. Oh look, now we need 71 people. To go up by, let's see, 99, 80, so that's what? Basically 20 of 80, so it's going up by 25%. 19 points, but that's 20% of, almost 20% of 80. We now need 71 subjects. Was it worth collecting twice as much data to go up by that much? Maybe. Maybe if you're trying to find something very subtle and something that's very important, and this is again when you start making judgment calls, you say to yourself, look, if this works, I don't know, we're going to cure cancer. Or some such. Okay? Probably not. Especially if it's your honors thesis or something. It's like you're going to look at that and go, oh good, now I can find an effect and I can test twice as many people. It's going to take me another 30 hours. That's fine. That should be fine. That'll be great. And believe me, if you, any of us, like, we're not running your study for you. And so, like, you're working with me and say, well, can you run some subjects? I'd look at you and go, no, I've ran subjects my whole life. I'm done, thanks. You do it. Do you want an extra 30? No, you don't. No, you don't. And it doesn't, the thing is, it's not like you're lazy. It doesn't help you very much. Like if this doubled your chance, but you look at that, twice as many people doesn't double your chances. Is it worth doing? Almost certainly not. For the kind of things that we typically do, right? So looking at, gee, I wonder if levels of processing affects priming and word fragment completion. Well, I better get as many subjects as possible because if I find this out, Nobel Prize, baby. No. No. Nobody cares. Right? I'm not trying to downgrade what we do. I think it's important and cool. I'm just saying that it's not curing cancer, so we don't have to worry about some of these things. All right. Questions so far? I know this stuff can be a little bit, you're also thinking backwards. Please.
It says it's the alpha power for 2 tildes. Now, I'm not able to connect the dots about getting delta by d whole square
Yep.
for the n.
Yeah.
So just trying to connect some dots as to how it relates with the t-test or something.
Oh, how this fits with the t-test is that the f and n part times d is how n affects the sample statistic. And we know that a t-test has square root of n in it, so we use root n. If this was analysis of variance, which it's not, but if it were analysis of variance, we would just use n. Because n is analysis of variance uses squared quantities, that's fine. So it's either going to be square root of n or n, almost always. And that's just because that's how it affects a t-test. Right? So this is how this thing affects a t-test, how this thing, and affects the test in general, is what you put in there. The nice thing is you typically don't even have to do these calculations. What you do is you go back, not this book, but sort of a graduate stats book, and there'll be what are called power functions and power tables. And you look and go, and they're graphs typically. And you just say, I have this many variables and this many, this is the design, and I need 14 subjects. Like, it's all set for you. So the logic of it's important. I'm never going to ask you to calculate this because people don't. Not that people don't because they don't and they should. What I'm saying is that typically they just look these things up, and it's really pretty straightforward. But yeah, it's root n here because that's how it affects the t-test. It's n if it affects it. If the formula for the thing you're looking at says n instead of root n, you use n. But it's pretty common that you need way fewer observations than you think you need. Almost always, you need way fewer observations than you think you need. Other questions? I hope that helped. Did it help? Okay, good. Because I rambled a bit there. No, that's what I do. Yeah.
Also,
Yeah.
We had a very subtle thing when we said d is equals to mu1 minus mu0 by variance.
Yep.
So when you said if you want to standardize this, when we say standardize, are we trying to say that when you want to use it for population just like we did earlier?
If you want to compare two different studies that are using different variables, let's say we have, let's make it really simple. Let's just say it's two things, and one is using Canadian dollars and the other ones are using euros. But your income should be affected the same way no matter what. If it's euros or Canadian dollars. But the variances are going to be different because they're different scales. So we standardize it by dividing by the variance or the standard deviation.
Okay.
That's just because the scales are different. Yeah. Other questions so far? One more slide. See, what I'm saying is there's diminishing returns to getting more subjects, and you don't always need that many is the important thing. So if you wonder what delta is, it's called the non-centrality parameter. We assume the null, right? Look, here's a T formula right here. We assume the null hypothesis. That's how this works. We start out by assuming the null is true, and we try to show there's no evidence for it. That there's evidence to reject it. Under the HO, so given the null hypothesis is true, the expected value of T is 0. Right? Because look at this. If there is no effect, the sample mean, on average, should equal the population mean. Right? If nothing happened, then the sample mean should equal the population mean. Make sense? If that's the case, then this thing, the expected value of this, would equal 0 if HO is true. Does that make sense? If there's no effect, then the two quantities are the same. We never get 0. We get 1 point something or whatever, or something. It's not significant because we don't tend to get right on the population mean. So that is how likely is it we'll find a value of t that is greater than t at 0.05. So in fact, this just has to be non-zero for there to be an effect. That's of course all theoretically. Obviously, it's not just non-zero. It's going to be greater than a statistic, than a significant value, etc. So if you're curious, that's what this is. It actually is calculated using the T formula. It's just saying that the difference between x bar and mu is non-zero. Okay. So you might wonder, Dave, why are you telling us all this? Did you say things like, I'm not going to make you ever do this? I want you to do calculations when you do your own work. I want you when you're talking to your honors thesis advisor next year. When you start, one of the things to say is, how many observations do you think I need to do? Right? And if you're using something like a 2x2 ANOVA, which a lot of them are like that, you probably only need about 15 people per group. You don't need 35 and 40. People seem to want, well, I get more power. Yeah, but there's diminishing return. Right? So very often you need like 12 or 15 people. And as I very commonly say to my honor students, if you can't find a difference when there's 15 people per group, do you think the difference actually matters? Or do you think it's like the size of your big toe being correlated to the size of your earlobe? Who cares? Right? So they're not hard to do, or just look things up. As I was saying, very often you just look stuff up. I'm pretty sure there are even online tools that will just do power calculations for you. Questions on this stuff? We can have a couple of questions if you want on those two after that. Okay. And we'll do this.